Okay, so I think let us start the post-tea session, and we have Professor Poonam Mehta from JNU, and she will be talking about a topic which we did not have discussed so far, which is testing foundations of quantum mechanics from neutrino oscillations.
Okay, I would really like to thank the organizers for inviting me here and also being kind enough to reschedule my talk because of certain situations that arose in my personal domain. So thank you very much to all the organizers for having me here, and I'm really happy to see so many of the students here who are participating in this school. And I will give you a very different perspective which you have not heard so far. And this is something which is not so obscure in current times, especially because there is a lot of emphasis on quantum information. There is something called quantum mission that our government has started. So there is a lot of emphasis and a lot of funding and a lot of resources are being put in that direction. So in all the fields, including particle physics, people are trying to see where one can overlap with quantum information, quantum computation, quantum technologies, because at the heart of everything, it's quantum mechanics. So whatever we are talking about, it's all quantum mechanics. So we will see how neutrino oscillations have overlap with foundations of quantum mechanics in particular, and what other things we can do. Yes, I will try to cover that at the end of towards the end of my talk, and then I'll be around so we can have some informal conversations afterwards. So actually, I should also mention that my interest in the subject is attributed to this place in Bangalore, in RRI, and Sam is here in the audience. So I got interested into geometric phases and foundations of quantum mechanics and having a broader perspective to doing physics in general because of Bangalore. And I hope some of you will take up something like this in the future. Okay, so here these are my PhD students. These have already graduated, and Sabila and Kritika are presently here, and she's also a new student. She's about to finish. There are also, this was a project student who came to me last year, and she worked on some aspects related to what I'm going to talk about, as well as Tanmay, who is now a PhD student at Colorado State University. Okay, and those of you who have not visited JNU, this is an invitation. This is a view from my office window. And of course, JNU is very beautiful, apart from what you hear in the news all the time. So please do visit us. Yeah, so the whole idea, whole interest in this whole subject has been triggered also because the 2022 Nobel Prize was awarded to Aspect, Clauser, and Zeilinger for experiments with entangled photons, establishing the violation of Bell's inequalities and pioneering quantum information science. And soon after, around the same time, there was also an ICTS program on horizons in accelerators, particle nuclear physics, and lab-based quantum sensors for high energy physics and nuclear physics, and which was a very timely workshop. So people are trying to intertwine, the developments in quantum sensors and looking at what one can learn in particle physics experiments. Okay, so the question that we are broadly going to ask is, what can precision neutrino experiments, because neutrino oscillation experiments have been going on for decades, and we have been getting more and more data. People are talking about doing machine learning with neutrino data and so on and so forth. So one would like to ask the question that we have already so much precision in these experiments. Can it reveal something about the foundational aspects of quantum mechanics? And let's see how we can address this question. So the plan of my talk would be as follows. I would give you an overview of foundational aspects of quantum mechanics, in particular the spatial and temporal correlations. And actually, this very simple-minded things like correlations can have profound implications on our view of the world. In particular, people, when there is a debate about what is a correct classical viewpoint versus quantum viewpoint, that all that can be addressed using correlations in the spatial or the temporal domain. So I will introduce the topic. In the high energy physics context, I will concentrate on the oscillations, neutrino oscillations, although it is not completely restricted to that. And I would talk about mapping of the two-state neutrinos to a two-level quantum system. Then I would come to something called temporal correlations in neutrino oscillations, which goes by the name of Leggett-Gerg inequalities. And we will talk about certain effects which are beyond the standard model, like looking for how one can enhance these violations, or if there are damping effects, what happens to these violations. And then using these temporal correlations, one can ask some questions which pertain to the domain of going to non-Hermitian Hamiltonians. And there can we address the question of Dirac versus Majorana. And I would also then point out that, in fact, it is not completely obscure what we are talking about. The precision experiments such as Minos and Diabe, two different classes of experiments, are actually reporting a very large violation of these Leggett-Gerg inequalities, more than 6 sigma, in their data. So they have actually analyzed the data and claimed that. Okay, and then we'll come to some recent works and then open for discussion. Okay, so because this is a school on neutrino physics, I would first start with foundational aspects, because that is something which would be new for you. So I would start the journey from the EPR paradox to Bell's inequalities to CHSH, and then to the Leggett-Gerg, how the historical development took place and what are the questions that were posed, and why is it interesting to look at these questions. So the whole thing started off around the same time when the quantum mechanics was being born. The question was about classical versus quantum viewpoint, which viewpoint is correct. There was a whole debate. And we know that the point of view that classical physics gives us or tells us is that the physical properties of an object exist independent of whether we observe or not. There is a well-defined property of an object, and the measurement process simply reveals that property. Okay. Whereas in quantum mechanics, there is no physical property that exists independent of the observation. Rather, physical properties arise as a consequence of measurements that are performed on the system. I'll give you an example. For example, in quantum mechanics, a qubit, which is an object you can think of a spin half, which can have plus or minus value, or if we look at the spin in the z direction, which is defined by sigma z operator, or spin in the x direction or any other direction, this value is revealed by appropriate measurement. It just gives us a set of rules which specify, given the state vector, the probabilities for possible measurement outcomes when the observable sigma z is measured, or when the observable, whichever is the observable, if we make a measurement, then only we know what the outcome would be. Rules are defined for us, but there is no well-defined outcome as such, like in the classical viewpoint. So the idea of EPR, basically they asked the question in 1935 that can the quantum mechanical description of reality be considered complete? So the question was whether quantum mechanics is the correct description of nature or not. Okay, so in order to address this question, okay, there are some statements here. I will read it and then I will break it up. The real factual situation of system S2, so there are two systems physically separated from each other. So what they said is that the system S2 is independent of what is done on system S1, which is spatially separated from the former. And the locality principle is motivated by special relativity, which forbids or prohibits instantaneous action at a distance. Such a principle was implicitly invoked in the EPR argument when it was asserted that a measurement on particle 1 cannot affect the condition of spatially separated particle 2, since there is no interaction between the particles. Right? So this is this was a statement. And then, however, it was found that even before making the measurement, one could predict what is the outcome on the system S2 by just making the measurement on the first. And in order to decompose all of this, we'll come to a singlet state, etc. They use the term element of reality to describe the physical property such that it is possible to predict with certainty its value just prior to the measurement. So this basically contradicted the view of quantum mechanics, according to which a particle would not have a definite value prior to the, or a property prior to making the measurement. Okay, so this is how the question was posed, and the assumptions were locality, realism, etc., which are heavy words, but basically what one is trying to say is that a realistic experiment which looks for EPR question was given by David Bohm in 1951, where he considered system of two atoms, each having spin half, prepared in a state of total spin 0. So you know that if we have two spin halves, we can combine two spin halves and generate either triplets or singlets, right? And one of the states which is carrying spin 0 is actually a singlet state, and this is possible for certain unstable excited states of diatomic molecules, etc. So it's not completely far-fetched. So singlet state is typically represented by this with a minus sign in between, and you have plus denoting spin up, minus denoting spin down, and the particles are allowed to separate when they are well beyond the range of interaction. We can measure the Z component of spin of particle 1. Because the total spin is 0, we can actually predict with certainty without disturbing the second particle that the Z component of the spin of particle 2 would have the opposite value. So this is saying that if you have an operator and if you have a singlet state which is actually written in such a form, then if I make a measurement on particle 1, I can actually immediately predict what the outcome would be for the second. So the value of sigma z to particle 2 is an element of reality according to the EPR criterion, and so are any number of spin components. So you could have sigma x1, sigma x2, and so on, or sigma some general direction also. So quantum state description is not a complete description of physical reality. That's what they concluded. And one could in general not only look at same direction or same, one could talk about arbitrary directions and again consider a singlet spin state vector and look at something which is sigma A cross sigma B. And one can find that this depends on the angle between these two sigma directions. So if it is sigma z, it will be -1, or sigma x, it will be minus perfect anti-correlation. You can say that if spin in z direction was +1 for particle 1, then for particle 2 it will be minus in the down spin or whatever. So sigma A here is the component of Pauli spin operator in the direction of the unit vector A, and this gives a general expression. And this correlation depends only on the angle between the two directions, sigma A and sigma B. If A is chosen along the Z direction, then one can actually simplify this expression and write it only in terms of sigma B. This is just a add-on. And then came the Bell's inequalities, in which John Bell revisited the EPR experiment in 1964 and came up with a set of inequalities which allow us to test the ideas of EPR. And there are two underlying assumptions here. One is realism, another one is locality. Realism means physical properties have definite value independent of observation. This is what I said when I talked about classical viewpoint. Locality means any measurement performed on A does not affect the measurement on particle B. Together, these are referred to as local realism. And to illustrate this idea proposed by Bell, so we are now getting to obtaining the relations that Bell obtained and which go by the name of Bell's inequalities. They talked about three people, Alice, Bob, and Charlie. Here I'm just calling them Aspect, Brout, and Clauser. There are three observers. We are having a setup comprising of these three observers. So Clauser prepares two particles, sends them to A and B, Aspect and Brout, one to Aspect and one to Brout, and there are some observables. Both perform two distinct measurements on the respective particles they receive, and sorry, here we go. And physical properties measured by aspect are denoted by PQ and PR, and by Brout are called PS and PT, and the values are denoted by QRST, which can take values plus and minus 1. So algebraically, one can obtain a relation which says that it is bounded by plus and minus 2, whereas if we look at the mean values, it says that if P is the probability that before measurement the system is in a state given by Q, R, S, and T, and this denotes the mean value of that quantity, then one can show that this is going to be bounded below 2. So this is the generalized form of the Bell's inequalities, which is also referred to as Clauser, Horn, Shimoni, and Holt inequality. And if we look at the singlet state example again, and take this QRST as specific, these are like the sigma x and the sigma z, specific combinations of these, then one can obtain this particular quantity can be at most 2√2, which is corresponding to the maximal violation of the CHSH inequalities. So Bell's inequalities, or the generalized Bell's inequalities, which go by the name CHSH, are violated, but they cannot be violated more than this. This is what is called the Sirelson bound. So they are between 2 and 2√2. Basically, the violation lies between. So quantum mechanics is clearly inconsistent with the Bell's inequalities. This implies that one needs to abandon either the locality principle or the realism, because this is what the arguments were based on. Okay. And then, so here the problem was that if you talk about Bell's inequalities, you are talking about spatially separated systems, and it's very hard to prepare two spatially separated systems with controlled things. So Leggett and Gerg in 1985 later came up with an interesting proposal where they said that we take a same system and make measurements at different times. Okay, so there it was making measurements at different spatial coordinates. Here it is with two different systems. Here it is a single system making measurements at different times. And here again there were underlying assumptions. One is called macroscopic realism, other is non-invasive measurability, which basically mean that if you have a macroscopic system with two or more macroscopically distinct states available to it with all times, will at all times be in one or other of these states. Okay. And the non-invasive measurability means that in principle it is possible to determine which of the state system is in without affecting the states or the system's subsequent dynamics. Now we know that classical mechanics conforms to these assumptions, but quantum mechanics does not, because quantum mechanics says that you have possibility of macroscopic superposition of states that violates the first, and the second one is the collapse under measurement violates the second. Okay, so naturally, if there is a quantum mechanical phenomena, it is expected that the Leggett-Gerg inequalities that we are going to show would get violated. Okay, yeah. So Leggett and Gerg inequalities bear strong formal analogies to Bell's inequalities. Even though there is an analogy, formal analogy, one should be careful, because in a Bell-like inequality, one considers measurements occurring on two or more systems at space-like separation, which I just said. And in LGI, one considers repeated measurements at different times of a single observable on a single system in a time-like rather than a space-like separation between the measurements. So how do we then get to the formalism of Leggett-Gerg inequalities? We consider an experiment with two possible outcomes. There is a dichotomic observable, which can take value plus or minus 1. There are only two possible outcomes that are possible. And then one can define, again, correlation functions, which is something everybody uses. So correlation function is defined, and then depending on whether they are perfectly correlated, anti-correlated, or there is no correlation, this Cij will take certain values. And if we look at a combination of theseCijs, the macro-realism restricts the following combination of two time correlation functions, which looks like this. And one can show that this k, depending on how many time slices we are making the measurements, so k3 is the minimal, k3, k4, k, if it is odd or even, it will give us some bounds on both lower and upper bound on these violation of these quantities. So if you look at this K4, it looks very much similar to the Bell's inequalities because there it was bounded by plus or minus 2. However, there is a difference between the two. There is a temporal measurement versus spatial measurement. Okay, so violation of this inequality implies that any one of the assumptions is not valid. Hence, the Leggettger parameter lying outside these limits are indicative of quantumness. And then the question is how far one can go for these violations. And in general, one can find these limits. That's completely straightforward to obtain. But then the question is how much you can violate. Again, there is a maximum upper bound, like the Sirelson bound 2√2. You cannot violate more than that. Okay, so so K4 can go maximum up to 2√2. K3 has a maximum violation of 3/2 and so on and so forth. So it will depend on the value. So if we have a two-level quantum system, which is where I will break up the neutrino problem to a two-level quantum system. So one can generally ask the question that what do we expect if we have a general two-level quantum system for these correlations or for this Leggettger quantity which is Kn. So there we can use the Pauli matrices for these Qs and so on, and it can be shown that if between these two angles An and Am or these two adjacent directions, if theta m is the angle, one can write down this whole expression in terms of just that theta. And the maximum violation can be obtained for a general value of n, and it can be shown that it depends on this quantity tau, which is nothing but T1 minus T2, difference between the two time slices where you are making the measurement. So K3 as a function of tau looks like this, K4 looks like this, because the variation can be just simply broken up into this form. Okay, so now having described the EPR to Bell's to Leggettger inequalities, I would come back to neutrinos because that's where we would like to apply these ideas and ask the question that how one can explore these questions using neutrinos. Okay, so neutrino oscillations you have heard in a variety of talks. I will just rush over the next few slides, but essentially what I would stress on is if we look at just two flavors of neutrinos, we have three flavors of neutrinos in the general standard paradigm. However, we can simplify the problem and ask the question if there are only two flavors, then the two flavor neutrino oscillations can be visualized as a two-level quantum system. And then whatever is the expectation for a two-level quantum system should just go through what we are saying in the neutrino context. Okay, so the idea of neutrino oscillations was given initially by Pontecarvo by looking at this K0 bar oscillation, looking at hadron-lepton symmetry. However, and at that time there was only one neutrino, so it was the only possible idea that could come was looking at a neutrino to antineutrino oscillation. However, soon after, these are the initial papers, sorry. Yeah. However, in 1962, Maki, Nakagawa and Sakata came up with the first proposal of actually the neutrino flavor mixing between different flavors of neutrinos. Around this time, the second type of neutrino was already known. So this involves two flavors of neutrinos, and this was their paper. And then Gribov and Pontecarvo also came up with this idea about two neutrino types after the muon neutrino was known to exist. Okay, so the question is, why do neutrinos oscillate? They are produced and detected via weak interaction. Weak states are different from the stationary states of the Hamiltonian. In fact, they are the superpositions of the stationary mass states, and that leads to oscillation phenomena. And whenever a non-eigenstate propagates, it leads to something which is very similar to birefringence in optics. It depends on the properties of the medium. And oscillations of neutrinos takes place even in vacuum, which is usually one requires for birefringence, one requires a delicate sensitive medium. Here one doesn't require that, it's only driven by non-zero mass splittings and non-zero mixing angles. In matter, oscillations are still driven by mass splittings and mixing angles, which get appropriately modified due to the charge current potential for the coherent forward scattering of the neutrino with the electron. And incoherent scattering cross section is usually very small. So one sees sustained coherence over astrophysical length scales, which is a direct contrast with the case of photons, where you can stop them very easily, right? So the two flavor oscillations can be described in terms of this mixing matrix. So you have these flavor states and mass states. They are connected to one another by this mixing matrix. This is a 2 by 2 matrix. We will actually look at a generalization of this towards the later part of the talk. But this is something one can think of only as an orthogonal rotation matrix parameterized by just one angle. And each mass eigenstate propagates as e to the, this is just the unitary evolution. And oscillation arises due to the phase difference that appears, which is dependent on delta m square, L, E, and theta. So the parameters of the two flavor oscillation are mixing angle and the delta m square, whereas the physical parameters of the experiment are L and E. And depending on that, you can actually see that the probability expression looks like this. Okay, so this is just a simple two flavor oscillation. One can visualize oscillations in a very neat manner, and the idea is that if you have two level quantum system, you can put all your states on top of a block sphere, or sometimes it's also called the Poincare sphere. It's just a two-dimensional sphere. So different states are points on this sphere. So if we put the flavor states as at North Pole and South Pole, then the mass states are tilted at an angle to that. And oscillation is nothing but precession of this flavor axis about the mass axis. And the resonance effect is something where your mass axis is lying here, flavor states are just going about, and so on. Okay, so that gives you maximal mixing. So somehow the conspiracy is such that, so everything one can visualize very neatly using this picture. There are different equivalent descriptions. So you are familiar with Schrodinger-like equation, which is something one obtains when you linearize the Dirac equation in the ultra-relativistic limit or paraxial limit. Then one gets a form like this. Whereas you can also have a density matrix formalism, where you define your density matrix and write it in terms of this commutator with the appropriate Hamiltonian. Or you can write down in terms of, this is again, one can write down a spin precession in a magnetic field equation by writing down Hamiltonian as B dot sigma and the density matrix of the neutrinos as P dot sigma. So there it is, B and P is precessing, B cross P is causing the precession. Okay, so it's P dot is omega B cross P, where B is not a real magnetic field, it is actually a pseudo magnetic field generated by the mixing angle theta. Okay. Okay, and the standard interactions basically do not do much, but there is some contribution that comes due to the coherent forward scattering, and in order to understand that, one can just look at this two-level Hamiltonian, and one sees that in vacuum you have this form without the VC term, in matter you have an additional term. MSW is nothing but vanishing of the diagonal elements of this matrix, where so you have VC by omega equal to cos 2 theta, that gives you the resonance condition. And what happens at resonance is something which is just avoided level crossing. So there are two energy levels, and here they come very close to each other. The delta m square becomes very small, the smallest possible that can happen, as the density is adiabatically changing. So this is the MSW effect, the two-level context. One can also again look at optical effects and their counterparts in the neutrino system. So you can write down the effect of a medium that can be described in terms of the Pauli matrices and identity. And depending on which coefficient is non-zero, different effects are obtained. So circular birefringence, linear birefringence, elliptic, and dichroism, which is absorption, are coming from various contributions which are just written in this equation. In the context of oscillations, you can see that in vacuum, A, C, and D are non-zero, matter also these are, and dichroism, which is absorption or such effects, they are almost negligible. So this is the contrast between general standard optical effects and neutrino effects. So one can just get the mapping correctly. Then one can ask the question that if neutrinos also exhibit birefringence or refractive property, can we actually make optical devices out of them? The answer is you can do a small calculation and find out if you take sun as a lens, the focal length is just given by this. And it turns out that if you take 10 MeV neutrinos passing through the sun with this density, it comes out to be 10 to the 5 times size of our galaxy. So potentially observable effects of small refractive index are possible only via neutrino oscillations. So it is a very sensitive interference experiment, albeit in the energy space. Okay. This was the 2 neutrino story. In reality, you have 3 neutrinos. So your mixing matrix is more complicated. You have 3 angles, 1 phase, and 2 delta M squares. And there are some unknowns which you have probably heard in many of the talks by now. Okay. So now we come to the question of merging the 2 things that I have just described. How do we do tests of LGI in neutrino oscillations? So there is a lot of work that has been done by other authors also in literature. So the whole story started in 2013 by Dipankar Home, Gangopadhyay and Animesh Sinha Roy. And it has been carried forward. Even there is a group in IIT Jodhpur and Uma Shankar at IIT Bombay. They have been interested in this topic. And recently also Amol and Dighe, they have been interested. Bindu Bamba has been working on topics related to this. So the general idea is to look for correlations or entanglement measure, or looking at whether one can think of neutrinos as qubits and quitrets, which is a well-known thing by now. But there are also questions which are saying that can we have a measure of testing for these quantumness or coherence properties of neutrinos, which is more profound or more what should I say, error-free than the Leggett-Gerg correlation. So there is a paper by Amol in which they describe quantum mismatch, which is going beyond the Leggett-Gerg measure. Also there is also no signaling in time. There is some other idea, which is also a paper which has recently come. I don't see it here, but it's there in my later part of the talk. Okay, so this essentially looks for that no signaling in time, which is a topic which is popular in quantum information context. Okay, so if we look at the 2-flavor context, we look at, you define a dichotomic observable, then the whole task boils down to looking for correlations, CIJs. So you calculate joint probabilities and so on and so forth. And then you compute the K3 and K4, and you see that the shape pretty much looks like what I showed you for the standard 2-level quantum system, right? Then one can ask the question that, we are also having precision in the neutrino oscillation experiments. So one is also being able to now look for subdominant effects, for example, due to non-standard interactions or something. So if there is a small tiny amount of subdominant effect, could it be hiding behind in our LGI signature, or could it lead to more enhancement, more quantumness or less quantumness, or such questions can be asked. What is the impact of new physics on violations of Leggett-Gerg inequalities? And this is something one of my PhD students who was not interested in doing standard phenomenology of neutrino oscillations looked at these aspects, and she looked at how do non-standard interactions impact these violations. Okay, so this is for the 3-flavor case. So looking at the dependence on the standard unknowns, I think I'll skip the details. So study of temporal correlations in the form of Leggett-Gerg inequalities has attracted interest in recent times. It should be noted that while different dichotomic observables have been employed, so all of these papers do not use the same dichotomic observables. So observables are free for us to choose. So different observables have also been used in the literature. The neutrino matter interactions were mostly considered to be standard. Non-standard is something we looked at. And then one also wanted to ask that if we have some damping-like effects, what happens to these correlations? And that has been also studied. So if you look at, so this is about non-standard interactions. I think this also you might have heard or will be hearing in some of the lectures. But essentially this is a modification of the Hamiltonian by an extra piece. I will not get much into the details, but if what is the implication of all of these epsilons on the standard oscillation framework, and then what is the implication on the Leggett-Gerg correlation and so on. So this is what something gave. Then there is something which is damped oscillations. You can actually characterize all kinds of damping effects through this parameter Dij. Look at the vacuum oscillation formula, which just looks like that. And this Dij encodes different classes of damping effects, which can be characterized, and those different effects can have different implications for the Leggett-Gerg correlations. So all of this can be done. Now, coming to the almost the final part of my talk, it is interesting exercise for everybody, all the students, that if you know that we take this is the mixing matrix, this as a, so cos theta, sin theta, minus sin theta, cos theta, right? But this is primarily due to the weak interaction Lagrangian, which basically couples the left-handed states. This is written for the quarks, but this goes through for the neutrino, for the leptonic sector also. So this is the mixing matrix essentially comes and sits here. So one of them is the up sector, one of them is the down sector, and this is the combination which is the U, PMNS. This combination in general, a 2 by 2 matrix which is unitary, we can write it in a general form like this. But it so happens that we have the freedom to redefine the states. So these states can be redefined if we can pull out some of these phase factors from this matrix. So you can pull out one of these factors here, one of these factors here, and then you can write it like this. However, this is for the true for the, if neutrinos are Majorana, there can be, even in the two flavor case, you can have an extra phase factor sitting over here. It so happens that in the standard oscillation framework, that Majorana phase will have no implication whatsoever at the level of probabilities. And that's why that is sometimes written or sometimes not written, but this is not the complete story. The complete story is that you could as well have a Majorana phase in two flavor oscillations. It's a different matter that Majorana phase is unobservable as long as we are talking about the standard oscillation framework. So there is so recent times, there is, not recent, in fact, this is a pretty old idea by Carl Bender, 1998 onwards. So he looked at harmonic oscillator Hamiltonian and slightly deform it by some parameter. So it's like p square plus x square times some factor I x to the power epsilon or something. So there it was found that if you have, so you are going to non-Hermitian domain, but you are getting real eigenvalues under certain conditions. That's a very instructive small exercise everybody can look at. And in the language of two-level quantum system, Tommy Olson and Zhou, they actually wrote down this general form of PT symmetric. So PT refers to parity and time reversal, as you may be able to figure out. And if you look at a general non-Hermitian Hamiltonian which respects the PT symmetry, then one can write down a general form of this. And if you look at just the symmetric form, then it looks like this. So if we just examine this general form, we can see that the eigenvalues and eigenvectors you can easily compute because you are just diagonalizing the Hamiltonian. It turns out that these eigenvalues can have a square root structure, and then depending on whether whether this term in the square root is positive or negative, you could have possibility of real or imaginary eigenvalues. Okay. So here the real eigenvalues are plotted as solid lines and imaginary ones are plotted as dashed lines. And the point where, and there will be some point where the lambda plus and lambda minus would actually become the same. So those points are something which are called exceptional points, and these are those points, this one, and this one. This is how it group goes. So this is something which is very much into the game in the quantum optics, quantum information, or even different contexts. So here it is also interesting, and main problem here is that for neutrinos the dichroism effects are very, very small. But if one considers the possibility of neutrino oscillations along with neutrino decay, which corresponds to adding non-hermiticity in the Hamiltonian, then one can actually mimic this situation. So then whatever one understands from the PT symmetric non-Hermitian Hamiltonians can be interestingly applied to neutrino oscillation physics, and this is what my students are looking at currently. We are just reviewing these papers and then trying to see where is it that one can go further. Okay, and this is another interesting idea which, so there was a paper by Khushbu Dikshit and Akhila and Uma Shankar, where they showed cleanly that if you take two flavor neutrino oscillations along with the possibility of decay, then this extra phase which I was just mentioning to you about, this e to the I phi, this Majorana phase, can play a role at the level of oscillation probabilities. Which means what? Which means that if one could think of an experiment where we could test this, then one could actually differentiate between Dirac and Majorana nature of neutrinos, which is one of the important open questions in neutrino physics. So using that idea, you can actually generate CP violation through the non-Hermitian piece. This is that gamma matrix. You can generate CP violation through this, or you can generate CP violation through the Majorana phase. Different effects through decay or Majorana one can generate. And then one can ask the question again, what happens to the temporal correlations? And this is what we studied, and we claimed that one could do a 15% discrimination between Dirac and Majorana depending on these correlations. So this is something which gives us a handle on something which one would not ever think that one could look at Dirac versus Majorana through looking at foundational aspects. In fact, both these domains have a strong feedback to each other. Sometimes one may understand some foundational aspects better looking at what precision data is telling us, or sometimes something is hidden inside the correlations and one can gauge from there what interesting. So there is a feedback between, it sometimes gives you a different perspective to what one is trying to say. Okay, so now I come to the final part of the talk, which is talking about the experiments, what experiments are telling us. So here is a snapshot of all the possible experiments that you can think of in the scale of L and E. So there are different classes of this also you have seen probably many times. Solar, geoneutrinos, reactor neutrinos, long wavelength, atmospheric, supernova, high energy neutrinos, that ultra high energy neutrinos, and so on, right? And if I plot it slightly differently, you can see that depending on what delta M square I am talking about, one can classify different experiments along these different diagonal lines. So reactor experiments are sensitive to this and also the delta M square 3-1. Whereas short baseline experiments, which are trying to look for sterile neutrinos and so on, or LSND, they are sensitive to the other larger mass splitting, which is 1 electron volt square. But most of the long baseline experiments lie on this line, and different experiments we can use any of these different experiments to address the questions that one is trying to raise. In principle, in general, the whole slate is open. So MINOS is one of the long baseline experiments. Here it is indicated. And if you look at MINOS data, so this was a 2016 paper, it's a PRL. So what the authors have done is they took the data and fitted it to the two flavor oscillation scenario. And within the two flavor oscillation scenario, the trick is that you want to look for different temporal slices, right? So data at different t, which means data at different values of L. Can we have a well-defined way of measuring data at different L? it so turns out, so I will just come to the next. So this is a 735 kilometer baseline, and what they have claimed is that looking at the survival probabilities of muon neutrinos produced at NUMI accelerator complex, this provides, so this is some other details. Okay, let me, so there is a difficulty because one needs minimum 3 time measurements for K3 parameter, and one also means, this also means that one requires at least 3 baselines with identical detection possibilities to infer the simplest of the LGI parameter, and it's impossible to practically realize 3 baseline measurement with identical conditions, you know. So authors in this paper, what they have used is that the phase factor has 2 experimental handles. One is, so oscillation formula has delta m square L over E. So L and E are coming in the same phase factor. One can mimic a corresponding change in L by looking at a corresponding change in energy. Overall, that's the same effect on the phase factor. So they actually binned the energy in different energies and looked at the spectral dependence and then concluded. So this is how they performed their test of LGI using MINOS by selecting different energies for measurements such that the phases obtained a certain sum. But this is done in the 2 flavor context. I mean, the data has been fitted to 2 flavor context, and then the winning in different energies has been carried out by the authors. So essentially, this is what I'm saying. The phase factor looks like delta m square delta L over E. Delta L can be mimicked by different energies such that energies follow certain sum rule. And then the K factor can be written in terms of these probabilities. So this violation, in fact, I mean, these inequalities have been violated in variety of contexts, but this violation in the MINOS data represents the longest ever range over which the Bell-like test of quantum mechanics. So it's a macroscopic distance Bell-like test of quantum mechanics that has been carried out. So it gives us a unique possibility in that manner. So this is again some details from that same paper. So here the deviation is 6.2 sigma. Observed number of LGI violations. From the number of violations, one would expect to arise from an underlying classical distribution. And I mean, the number to remember is more than 6 sigma. That's good enough. But and the trick that was followed by the authors. Similar trick has been followed by another set of authors in 2017, right after that paper came. And again, 2 flavor, but they have looked at the Diabé experiment and found that again the violation is large, more than 6. Okay. So if we look at data in neutrino oscillation from oscillation experiments, in general one would expect, because oscillations is a quantum mechanical phenomena, and anything that's quantum mechanics is expected to violate these inequalities, right? That's what is the underlying thing that one is. So, but then to how far it is violating, then the question is how much we can evade that. Can we go beyond this, the bound that is coming due to quantum, that Serelson bound, or what are the best ways to make the measurement so that we can test the quantumness more precisely? So can we think of different measures? Can we look at different experiments or combinations of those experiments and conclude something more about foundational aspects or the quantumness or the coherence properties of neutrinos? Okay. So this is really the last part. I've been saying last part. So this is something, this is some recent work. So this is some food for thought for the younger people. You can actually, so this is the paper which talks about a different measure of quantumness, which goes beyond the Leggett-Gerg. So this is one paper you can actually look at, and the claim is that the quantumness can be probed more effectively, albeit it is using the survival probabilities for this discussion. Then there is also this, I was telling you about no signaling in time as a condition for macro realism. So Leggett-Gerg inequalities depend on something called macrorealism and non-invasive measurability. And these two underlying assumptions, sometimes when one is trying to define a observable or a dichotomic observable, one is relaxing certain of one of the conditions. So can we have more precisely fitted macrorealism and the other condition? So no signaling in time is something which is considered superior to the standard way. So here these authors have looked at this. So it goes beyond the Leggett-Gerg. This is the archive reference. This is again another paper which talks about genuine tripartite entanglement in three. So naturally, if you talk, we were talking mostly about the two-level system, but if you have three flavors, you have three-level quantum system and so on, or n level one can go to. So so there can be genuine effects which are tripartite by looking at three flavor oscillations, and these authors delve into that. This is again another paper which talks about Leggett-Gerg inequality in reactor and accelerator experiments. Again, idea is very similar to what Minos and Diabe guys have done. So this is something which relies on that idea, but it's like a more comprehensive. It will summarize both the set of studies. Okay, so here is the reference for that, and there is also something which actually Sushant pointed out during the web. There is this paper which came up in 2022. So here there is a measure of concurrence which leads to a prediction for the value of delta Cp. So one of the unknowns in the neutrino oscillation physics is the Cp phase, the Dirac Cp phase, and concurrence is a quantity that is defined in the quantum information context to signify what is the measure, what is the quantumness, or what is the measure of entanglement. And that can actually, if you minimize the concurrence, you are saying the authors have claimed that they can make a prediction for the delta Cp, and their conjecture is that minimum entanglement leads to the PMNS parameters and so on, and Cp conservation is favored. So this is something also interesting in this direction. I should have put web. This is from the earlier slides. Okay, this is another interesting thing where this is something which I heard a talk by Radhika Watson, where people are trying to give measures of, so concurrence is one quantity, entanglement measures are different, there are different ways of quantifying entanglement or quantum tests in general. So there is a generalized geometric measure, genuine multipartite concurrence field, and then geometric mean of bipartite Riemannian entanglement measures. So in general, this subject is very rich and interesting, and I think it does intrigue me. I don't know which direction I will go further, but this is also something which is an open slate. Not many people are working on this. So looking at different entanglement measures as a more general physics topic in particular. Okay, I think, so this is about different entanglement. Okay, so this is my, how am I doing in time? I'm almost, oh, okay, almost. Okay, so summary of the talk. Let me just, if you missed a beat, let me just summarize. So foundations of quantum mechanics is an active area of research widely used in optics and electronic context so far. But even in particle physics, in fact at CERN also there is a quantum technology initiative, a center that has been formed recently. So most of the particle physics labs also are looking at the cross connections between, even there are new ideas that are emerging for looking for dark matter, low energy dark matter using some different superconducting qubits and so on. That sounds also very interesting and intriguing. But okay, I have not read much about it, but that's something which is also happening in the. So neutrino oscillations provide an ideal platform to look for such violations at macroscopic distances that might not be accessible in other contexts. So when we are looking at different systems, we should also highlight and contrast what is the strength and what is the weakness compared to other contexts. So especially compared to optics and other electronic contexts, we have strength in saying, because we can go to macroscopic distances which are just not accessible by other means. And then foundational aspects may allow for indirect tests of new physics scenarios, such as non-standard interactions, etc. High energy experiments, specifically oscillations, have reached the level of precision that allow for stringent tests of temporal inequalities of the Legend-Gerd type. And one can actually look for nature of neutrinos, or maybe some other questions, smarter ideas can emerge. So far, experimental efforts have used simple two-flavor case. It would be interesting to use the data with all three flavors to see the impact on the violation of LGI. I think they are probably going to do it. It might be more cumbersome to do so. Thank you for your attention. So questions?
Hello. Okay. Ma'am, when you talked about PT symmetric Hamiltonian, so when you write a Lagrangian, it should be PT symmetric also, right?
You put in the constraint, you check for the PT.
So now the Lagrangian has to be charge conjugation symmetric also to preserve a CPT. So that means that Lagrangian inherently says that particle is equals to antiparticle if you quantize that system. So isn't that Lagrangian inherently saying, if you write for like neutrinos, isn't that Lagrangian inherently saying that the neutrino is Majorana in some sense?
That's interesting. Let's think about it and answer. I think what you are saying makes sense, but so if it is a PT symmetric, you are saying it doesn't automatically.
For the CPT symmetric.
It's an interesting question. I just need to think a little bit before giving you a definite.
Okay, thank you.
The Bender Olson. It doesn't say anything. It makes logical sense.
Actually, they just took the
They just took the form. Yeah.
With that, they went to it. They didn't talk much about the Lagrangian.
Did not talk about CPT, in fact. But in general, yes, CPT should be conserved, and if it is so, then PT symmetry implies C. Logical, yes. Good question.
Hello, ma'am. Yeah, actually, maybe it will be a naive question. Like you, in your one of the slides, you make about that K3, K4 maximum value. So like it should not be go beyond the 3/2 or 2√2 something values.
Yeah.
So like, I mean, the violation should not be go beyond that value. So like what will happen if it will be found that the more than that values, like will
That
it be
is
the again?
That is not attainable. That is the thing. You can compute those numbers come from imposing certain restrictions on the correlations. It does not go beyond that.
So what will be the physical significance?
Yeah.
I mean, it will be again the classical mechanics phenomena or something?
That will only say that. Yeah.
It will disprove quantum mechanics if you violate that.
Yeah. Yeah. So that's what comes from quantum mechanics. Yeah.
And then does it saying so that like our neutron oscillation quantum system is coherent or decoherent something?
Say again. You are saying look at the different KNs.
Yes. So
Yeah.
The degree of LGI violation. Does it say something about the coherence of our quantum system? So I wanted to connect the coherence in the oscillation sector to the LGI violation. So does it? I mean, I'm not sure if the questions make sense or not.
So quantumness and coherence are connected.
Yes. So and then
LGI
quantumness.
violation looks for quantumness.
Yes.
So
So
it
that's
also indirectly looks for coherence. Right?
So let's say if we observe or let's say there are LGI violations in the two flavor system. So then can it say something about the coherence of the this neutrino quantum system?
It will say, no?
So I mean, if it is coherent, then how much does it violate the this
Can one
decoherence?
set limits on decoherence?
Yes, that's what.
Probably you can, yes, to some level, yes. What you are saying is look for deviations, and then depending on the deviations, can we put stringent bounds?
Yes, that's.
One can.
Okay, I think that, Sam, you want to say something?
Just one question.
Oh, please.
So you gave a number for the length, the focal length of the neutrino for the sun as a lens, no?
Yes.
Is there a number for the decoherence length, the length scale over which the wave functions gets decoherent? For example, inside the sun, is there a calculable number for that?
There should, one could probably calculate. I have not done it, but I think there should be. It should be possible.
Thank you.
It depends on what kind of decoherence one is talking about, wave packet decoherence or some other kind of decoherence. And there, I think there are numbers available. I think Smirnov and
Packet decoherence connected to the process of the sun, at least that length is calculated. And the thing is that the matter effect actually spoils the coherence. But when they are propagating as the mass eigenstate, then the coherence is. But for the sun, the distance is such that the delta m square term is not there. Like for the say the 8 m, 10 m, 5 m is a boron neutrino. So then what happens is that term is not creating any problem.
But we don't need any neutrinos to do the coherence, because once the neutrinos out from the sun,
yeah, they are actually incoherent.
the distance is so large.
Yeah.
Like for
Over-
solar neutrinos, for any high energy cosmic neutrino, the wave
It is incoherent propagation.
they are already separated.
Yes.
Because whatever mass
Basically, phase factor is averaging out there.
I will take one last question. Shailesh, you had a question? One question you can ask.
Yeah.
Making a singlet state out of the two spin half
Spin half,
atoms.
yeah.
So, and then you say that even after separation, if measuring the spin of one state can infer the spin of other atom. So I was just like confused, like at what state do we still call it singlet state? Like we are separating them,
No. So
we
I
can
will
separate
tell-
them to infinite
No.
distances. So.
So I'll come to that 1 minute. This is what we said, no?
Yeah.
Take the singlet state, then I will come to the next slide 1 minute. So, when you look at correlations, you look at a quantity like this. So it could be sigma A, sigma B, two different directions, or it could be sigma Z. If it is sigma, so sigma A is in general two different directions. If there are two different directions, you get a angle here, minus of cos theta. If they are the same direction, then you get -1. So essence is that this singlet state over which we are making the measurement is important. If we had a separable state here, you would not get the correlation. So entangled singlet state is an entangled state. That's why it is giving us a perfect anti-correlation. That is the essence in the argument. We can talk more later.
Yeah, we can continue further discussion and we have to finish it here.
Yeah.
So